Hello to everyone. Myself is Dr. Vadiraj Tangod, Assistant Professor, Sri Jagadguru Tontadare Government First Degree College, Mundarbi. My today's discussion is continuation of crystal structure. This is session number 4. This session is specifically concerns to the BSc program, Physics paper number 1, 6th semester, syllabus to the Karnataka University, Dharwad. This session I am dealing with Miller indices, interplanar spacing in the crystals, and few numerical problems solved on this discussion. Learning objectives of this session is to understand the concept of Miller indices, how to write the Miller indices, concept about the interplanar spacing, concept to write, how to write the Miller indices, and solve few numerical problems on the Miller indices and interplanar spacing. Session outcomes. We know we will get complete picture about the Miller indices, understanding how to write the Miller indices, clarity about what do you mean by interplanar spacing, and how to solve the numerical problems on the Miller indices and interplanar spacing. Prerequisites for this session is concept about the crystal structure, various lattice parameters, idea about the Miller indices. Now Miller indices. What do you mean by Miller indices? Definition for Miller indices is reciprocal of integers. They are made on the intercepts made on the rectangular axis is called as Miller indices. These are pure numbers, these are integers. How to write the interplanar spacing intercepts and how to write the Miller indices, we will have certain steps. First step is we should be fix the coordinates which the plane intercepts makes on x, y and z axis. In denoting the intercepts, if the plane is parallel to an axis, intercept is taken as infinite. If the plane passes through the origin, choose an equivalent plane or move the origin. Second step is take the reciprocal of these intercepts. Third step is make an integer, put it in the curly bracket or square bracket. They are called HKL. They are called Miller indices. Therefore, Miller indices are the integers which are made reciprocal of the intercepts made on the three rectangular axis is called Miller indices. See here one example. So the blue area it covers, we have fixed up the coordinates x, y, z. Along the x-axis, the blue area it intercepts on the 2, and along the y it meets at 3. Along z it meets at 1. First we should be write intercepts. Find the intercepts along axis. It is 2 along x-axis, 3 along y-axis, and z along z-axis, 1 along z-axis. Now reciprocate it. 1 by 2, 1 by 3, 1 by 1. Third step, convert it into the smallest integers by multiplying the factor, LCM factor, it is by 6. Then 1 by 2 it is multiplied by 6, it becomes 3. 1 by 3 multiplied by 6 it becomes 2. Then 1 multiplied by 6 it becomes 6. Therefore 3, 2, 6, these are the integers which are reciprocal of intercepts made on the three rectangular axes. They are called Miller indices. They are represented by the letter H, K and L. Now we will write another example here. If suppose this is one intercept made on the three rectangular axes, A1, A2, A3, these are the axes. Intercepts are 3A1, 2A2, 2A3. Therefore, intercepts are 3, 2, 2. Make it reciprocal 1 by 3, 1 by 2, 1 by 2. And multiply by 6. LCM is 6. Therefore, multiply by 6. It becomes 2, 3, 3. Therefore, put it in a bracket. It is 2, 3, 3 is the Miller indices for the intercepts 3, 2, 2. Now we will see the few examples, few numerical problems, how to write the intercepts. First, pink color in itself we can take it. It intercepts along x-axis is 1. It does not have the intercept along y-axis, therefore it is parallel. We can write it as infinite. Z-axis, it does not have the intercept, therefore we can take as infinite. And reciprocate it 1 by 1, 1 by infinity, 1 by infinity. Make it integer. 1 by infinity is 0, therefore 1, 0, 0 is the Miller indices for this pink color unit cell. Take green color unit cell. It has an intercept along x-axis at 1. Y-axis is also intercept at 1. There is no intercept along z-axis, therefore intercept may be at infinity. Then reciprocate it 1 by 1, 1 by 1, 1 by infinity. 1 by infinity is 0. Make an integers, therefore it is 1, 1, 0 plain. It is called in Miller indices for this green color unit cell is 1, 1, 0. Then red color, you can take red colored unit cell. It is intercept along x-axis is 1, y-axis is 1, z-axis is 1. Therefore 1 by 1, 1 by 1, 1 by 1. Therefore Miller indices are 1, 1, 1. Now there are various examples how to write the Miller indices for these planes. First 0, 0, 1, it is Miller indices. So how it is? Intercept along x-axis is infinite, y-axis is infinite, z-axis is 1, therefore Miller indices is 0, 0, 1. In this way, we can write various Miller indices. We can try these Miller indices for these various examples. Similarly, we have so many examples of the writing for the Miller indices. If it is intercepts made along the negative axis, minus x-axis, then you should write it as bar 1, bar sign with a bar sign. It intercept, it gives the meaning of the along the negative axis. In this way, these are the few examples. Bar 1, 0, 2 Miller indices for this plane, 1, 0, 1 Miller indices for the second example, 1, 0, 2 for another, 1, 0, 2 and 2, 0, 1. This is a mix of the plane. We have the Miller indices. So this is all about the Miller indices. Now we are passing on to the another concept called as interplanar spacing. We know planes are exactly, in the crystal structure there are so many planes, they are like a slicing of the cucumber. Therefore interplanar spacing is the distance between the two successive planes is called interplanar spacing. Here H, K, L are the Miller indices, A, B, C are the unit cell dimensions. Then interplanar spacing is given by 1 by D is equal to 1 h square upon a square plus k square upon b square plus l square upon c square raised to half, or you can also be written as 1 by d is equal to square root of h square upon a square plus k square upon b square plus l square upon c square. Or you can write 1 upon, instead of 1 upon d, you can write also d is equal to square root of a square upon h square plus b square upon k square plus c square upon l square is also written as interplanar spacing. This formula is changes according to the our previous lattice. For cubic structure, we know A is equal to B is equal to C. Therefore, instead of writing B and C, we can make it as A. Therefore, h square upon a square plus k square upon a square plus l square upon c square. A square is common factor. Make it reciprocal. Therefore, interplanar spacing for HKL Miller indices is A upon square root of h square plus k square plus l square. In this way, the interplanar spacing formula will be changes depending upon the our unit cell we have chosen. Cube it is different, orthorhombic it is different, tetragonal is different, triclinic, monoclinic, orthorhombic, tetragonal, cubic, trigonal, hexagonal, rhombohedral. Depending upon the previous lattice, this formula will be changes, and accordingly we should be prepare the formula, and you should be substitute the values, then you should be calculate the interplanar spacing for a particular unit cell. Now, crystal structure of sodium chloride. Sodium chloride belongs to cubic structure. In the cubic, it is face-centered cubic. Here, sodium atoms are represented by red colors. Chloride atoms are represented by blue color. So, chloride, they are the anions. They are larger the radius than the cations. Therefore, we have shown the anions, negative ions in a bigger size and cations in a smaller size. And arrangement of these atoms are, sodium atoms are alternatively they have been arranged. One right, sodium, next blue, it is chloride, again red. In this way, atoms are arranged successively one by one. Therefore, alternatively it has been arranged. Therefore, sodium chloride crystal structure is face-centered cubic. Sodium atoms, they are smaller in size, its radius is small. Chloride atoms, their radius is large. We have shown in the bigger size. It has been shown you the alternate arrangement of the atoms one by one. Therefore, it is called sodium chloride crystal structure. Next, another example is crystal structure of cesium chloride. Cesium chloride belongs to body-centered cubic. Again, chloride is larger in size. Chloride is at the body center. Cesium atoms at the corners of the 8 edges of the cube. Therefore, it is called body-centered cubic. It is called cesium chloride. Sodium chloride belongs to face-centered cubic. Cesium chloride belongs to body-centered cubic. Now we will see the few multiple choice questions on our discussion. Sodium chloride belongs to simple cubic, body-centered cubic, face-centered cubic, all of the above. Correct answer is face-centered cubic. It is FCC. Answer is C. Cesium chloride belongs to simple cubic, body-centered cubic, face-centered cubic, all of the above. The correct answer is, it is body-centered cubic. Answer is B. So if you have any questions, you may put the questions in the comments box, and we will be answer for a particular questions. So thank you for watching all the series of the 4 series of the crystal structure. Thank you one and all.